Hello and welcome to this video. Today we will solve the exercises 42 and 43 from the chapter 3 of the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. The statement of 42. Question 42 is, let G be a group and let A belongs to a G, an element of group G. Prove that the centralizer of A and centralizer of A inverse are equal. Okay, we start the proof. Let X belongs to the centralizer of A. By the definition of centralizer of A, whenever an element belongs to the centralizer, then it must commute with A. This means this X A is equal to AX. We multiply both sides by A inverse. A inverse X A is equal to A inverse AX, and similarly, okay, because this A inverse and A are multiplying with each other, so it will be identity, and it will be A inverse XA is equal to identity into X, and that will be A inverse XA is equal to X. Now we post multiply with A inverse, and this will be again identity, and what we will have A inverse X is equal to X A inverse. This shows that X is also being commuted with A inverse. This means this X belongs to the centralizer of A inverse, but as this X was arbitrary element of centralizer of A and now it belongs to centralizer of A inverse, this implies that centralizer of A is subset of centralizer of A inverse. Similarly, we consider let Y belongs to the centralizer of A inverse. It means Y must be commuting with A inverse. This means Y A inverse is equal to A inverse Y, because Y is belonging to the centralizer of A inverse. We multiply both sides by A. AY A inverse is equal to A inverse Y, and what we will have in the similar way is equal to Y, and now post multiply by A. We will have AY is equal to YA, which shows that Y is also commuting with A. This means this Y belongs to the centralizer of A, and this Y was the arbitrary element of centralizer of A inverse, and now it belongs to centralizer of A. This means the centralizer of A inverse is subset of centralizer of A, and if we combine these two inclusions, this one and this one, we will have the equality. This means centralizer of A will be equal to centralizer of A inverse. Alright, we move to the next question. Question 43. The statement is that for any group element A and any integer k, show that the centralizer of A is subset of centralizer of A to raise power k. Use this fact to complete the following statement. Statement is, in a group, if X commute with A, then we have to complete this statement. And the last part of question is the converse true? Okay, let's start the solution. We will use the mathematical induction let k is equal to 0. This means A to raise power k means A to raise power 0 will be identity. Clearly C of A will be subset of C of a to the power 0, which is actually C of E, and we know that every element commutes with E, and this will be whole G. So it is true, the fact is true for k is equal to 0. And let k is equal to 1. This means centralizer of A is subset of centralizer of A. It is also true because every element or every set is subset of itself. Alright. Now we have to show that result is true for all k. We assume by mathematical induction, because we are using mathematical induction, we assume the hypothesis, let the result is true for k minus 1, that is the centralizer of A is subset of centralizer of A to raise power k minus 1. And now we have to show that this result is true for k. Let x belongs to centralizer of A. This means this commute with A, xa is equal to ax. Now consider x into a to raise power k, and that can be written as x a to raise power k minus 1 into a, or we can write it as x a to raise power k minus 1. Because x is commuting with a, this means this will be ax a k minus 1. And since this x is commuting with a, this means x belongs to this set, and this set is subset of centralizer of a to the power k minus 1. So this x also be commuting with a to the power k minus 1, and we will have a into a k minus 1 x, and that will be equal to a k x. This means this x must belong to centralizer of a to the power k, and because this x was arbitrary element from the centralizer of A, this means centralizer of A is subset of centralizer of AK. Alright. This implies result is true for all k greater or equal to 0 for negative integers. The proof is similar because from question 42 we know that centralizer of A is equal to centralizer of A inverse. Alright. Hence C of A is subset of C of AK for all integers OK, means for all k. Now the complete statement which we have to complete in a group if x commute with A, then x commute with a k for any integer k. That is the complete statement. Now we have to check that is the converse of statement is true. We have discussed many times that to prove a result we have to prove the general, but to disprove a result we just need a single counter example. Alright, let take the group Q4 quaternion 4, and if we take A is equal to I and x is equal to j and integer 2. Now we take a x square which is equal to I times j square. We know that j square is equal to minus 1 is equal to minus I, and we know that minus 1 into I is equal to, again we can write minus 1 to the j square into I is equal to x square a. This means a commute with x square, but ij is not equal to ji in general. In this group quaternion 4, this means ax is not equal to xa. So we can safely say that ax square x square a does not imply ax is equal to xa. Hence the converse is not true. And that is all about today's lecture. See you next time.